scientist at Dave. So Dave is a fintech organization. So it's a banking and fintech organization. So primarily as a data scientist, I work in underwriting and approving micro loans for users. So I do have quite a lot of experience with in different parts of the whole process. So be it data analytics, machine learning, modeling, putting models into production, and then monitoring the models, and then building dashboards, reports. So end to end, I've been working at different parts of the whole data science pipeline. So coming into why I chose this topic of applying data science in industries. So a short story about this is when I was doing my master's at USC, the way we used to develop models, train them, and then evaluate them was a total different story to how we do it in an industry. So we have industry specific tools. We have, it is totally different from the way in which we research, develop a model to deploy it and putting it into production and seeing in live what happens, how a model reacts or predicts different types of data. And the whole process is completely different. So I thought I would give you an overview of how we could apply data science in industries. So today's agenda is basically looking into the industrial ETL pipeline and beyond. So ETL is extract, transform, and load. So that is a pipeline which is most at an industry level standard, and what we do with that. And then next we're going to look into what are the simple steps that we generally use to create a machine learning model. And then I'm going to look in, show some sample code in Python. So for data science, mostly we use either Python or R as a programming language. So if most of you are unfamiliar with Python, I will go ahead to explain it in a little bit detail. But that's going to be a very simple Python code example. And then I'm going to show how the same code is in research phase as compared to when you modify it to deploy that particular model. And then we look into how and where data science and data engineering integrates, and how we can monitor the model performance that once we put it into production. And we'll also look into how to monitor and calculate data drift, and about industry standard tools and technologies in data science. And then we'll have about a 15-minute session for Q&A. So with ETL pipeline, let's just start with a very simple example. So if we take any application, so I think WhatsApp is an application which almost everyone would be using on a day-to-day basis. So in this application, what happens is a user sends a message and a user receives a message. So this is happening in live. So we consider the application to be WhatsApp. Then you need this data to be stored in a server. So if one person is sending data and one person is receiving it, we do have enough time to basically send the data, process it, and store it. But imagine millions of people across the world are sending millions of messages every second, and so there's a huge amount of data coming in. So on the server, there could be just a streaming service which could just push all the data that's coming in live and store it into a backend database. So the database could be traditional databases, it could be MySQL or any other traditional database which could store data. So once the data is stored, we basically use ETL tools to put it into a data warehouse storage. So a data warehouse storage, how is it different from a normal database is, this data warehouse storage can basically store structured, semi-structured, unstructured data. So when I say structured, it's basically something which is very similar to a SQL database, or which has rows and columns. When I say semi-structured, You can imagine something close to XML data, where some of it is structured, some of it is not structured. And then when it comes to unstructured data, it is like, it could be any file. Just imagine a PDF file, it could be any data, it has no structure at all, and you have that type of data. So when all of depending upon whatever data comes through the application, we could convert it into structured, semi-structured, unstructured formats of data and store it. So how does this transformation basically happen? So that what the data that is in the database is basically raw data, and what that raw data needs to be transformed into one of the three forms of data. So for that purpose, we use ETL tools, which could be, MapReduce, Hadoop, Apache Spark. It could be any of those, where it, does certain jobs and transforms this raw data into one of the three types of data, and then puts it into a data warehouse, a storage basically. And this is where the data is generally used for different types of application purposes. So when I say application purposes, it could be used mainly for three things. One is analytics, second is reporting, and the third is machine learning. So when it comes to analytics, so let's imagine the same WhatsApp application, right? In an industry, there could be like a lot of analysis that needs to be done on so what is the time between the time a user sent a message and the time the user received a message. So that is a very simple thing. The time difference could be in milliseconds. And there could be a lot of analysis around what is the mean, what is the median, what is the standard deviation, and what are outliers. Are there any messages which take a really long to deliver to a particular to a specific set of users? So there are a lot of analysis that could be done with the data. So this analysis could be done basically in SQL, or it could be done on using Python code, R, or any of the analytics platforms. So this is something which depends upon in company to company, but we could do different types of analysis in different ways. So the second is reporting. So this reporting, what I mean by reporting is basically to look at daily stats, weekly stats, monthly stats, to see if everything is as expected. So this could be something related to how probably WhatsApp has an update today, and then there's a version update, and we want to look at all the reporting metrics, probably number of active users, a number of users in each country who are active, and so many other things. So those are all reporting metrics which can be used, which can be developed using some of these reporting tools. And this could this reporting generally means we look at it in a visual format. So it could be bar graphs, it could be scatter plots, it could be lines, it could be pie charts, it could be a combination of any of these things. It could be more complex reporting as well. Sometimes it could just be tables where we just report certain type of data. So reporting could be different varieties as well. And then comes machine learning. So machine learning by itself is a whole different concept, where you use the data that you have to predict something, and that could have a large variety of things. So as I said, analytics, mostly it is data analysis, SQL or code, and reporting is mainly building dashboards. So when it comes to machine learning, it's these four steps as I as the four major steps I see. So one is model development. So this is a phase where we get some trained data, we build a model, we develop it, we test it, and it works fine. So this is like a research phase. And then when we go to the model deployment phase, it is a phase where this model is actually going into production. It is going to be live to a lot of users, to a large user base. And this model is going to actually perform predictions in live and then send back data. So, and then once the model is put in deployment, we don't know how well the model is performing. Is it performing good? Is it performing not as expected? How does it actually perform? So for that perspective, we need to always have a data monitor, which kind of monitors the type of data and the data flowing into it. And and I'm going to cover that topic in detail later. And then once the data is being monitored, we need to find out if there are any anomalies, and then go for checking if there is a data drift. And if there is a data drift and we identify the reason for the data drift, we could either retrain the model, or we could go ahead with trying to remove that particular data drift, how to rectify that particular data drift without retraining a model. So this is a process which always keeps going on and on and on. Once a model is put into production, this model very rarely stays without being retrained for a long time. And we're going to cover most of this part, this model development, model deployment, most of that part in today's session. I'm just going to go over the steps to create a machine learning model. So first is data pre-processing. So imagine we have some amount of data. What data can we take? Okay, let's just assume we have some amount of data related to predicting the sale price of a particular home. So we have data related to, the day of listing, then, the number of bedrooms, number of bathrooms, square feet. And then we have a lot of data related to sale price, street, all of that sort of data. So with this data pre-processing step, this generally means it handles missing data and removes outliers. So when I talk about this, let's say like we have a data set with 20 columns and a predictor variable. So in the 20 columns of data, if one column has just, if there are about 1 million rows of data, and there are only about 1,000 rows of data which has values in a particular column, so that column generally does not contribute towards predicting a value, because almost all the other rows have nulls. So it is safe to remove that particular column. So because we don't need that in predicting as a predictor variable. So the second thing is when certain columns have a lot of missing data, which means like, probably in 1 million rows, probably 900,000 rows would basically have data, and then probably 10% does not have data. So when 10% of the columns don't have data, we generally have to fill it with some data. So let's say it's a numeric column. We could either fill it with zeros, or we could fill it with the mean of the values in that particular column, or we could fill it with the mode of the values. So it depends on what type of column is it and how do we want to fill that particular value. So and then sometimes we need to also remove outliers. So when I mean outliers, let's say all the let's say a house is generally less than 3,000 or 4,000 square feet, and if a few rows have the square feet to be about 12 acres or 200 acres, those are all outliers which are extremely high values. And sometimes we may have data which could be like negative 200 square feet, which is not actually a proper form of data. So we need to remove all those data which we think as outliers, which do not contribute towards a proper trained data set. So these are the ways that we generally do the pre-processing step. So any data that we get, we generally have to see what that data looks like and pre-process the data before we could do any other type of training. So next is the feature engineering part. So when I talk about feature engineering, this has different steps. So you could create derived features, you can handle collinearity and adding extra features. So when I say derived features, let's assume that there is a date column, and let's assume with the date you want to predict seasons. It could be summer, winter, spring, fall. It could be any of the 4 seasons. So it is very important that a date column is transformed into a month and a quarter or a year or something like that. So and if we sometimes date columns come with date and timestamp. So it has a date followed by hour, minute, second column, which needs to be like divided into and see if hour, minute, second, is that going to contribute towards anything? If not, we could remove that. If it's going to contribute, we could like calculate derived features. So, and when we are creating derived features, it's very important that we handle collinearity. Let us say we have a column X and we have a column Y, and the column Z is a derived column from X and Y together. So Z is equal to X plus Y. So it's important that we should not have all the three columns, because a column which could be derived from a set of other columns needs to be handled properly, because this would lead to overfitting. And so we need to handle this particular collinearity where we need to remove one of the three columns. So if we have two columns, and then we're adding a new column, we need to make sure one of the two previous columns have to be removed. And we could also add extra features. Like, for example, we while building a model, we just thought like this feature is not important, we don't need to add it. And then over, after training, probably thought maybe this feature is important. So probably we could add this extra feature. So it's a combination of all of these things. That's what feature engineering does. So now is modeling and training. So here we basically choose one of the three. So when we talk about training a model, it's either a classification, regression, or a clustering problem that we're trying to solve. So what is classification? Classification in general is something where it's like a yes or no, or it's kind of giving a label. So if it's a yes or a no, it's called two-class classification. If it has more than two target values, like spring, summer, winter, fall, then that's called multi classification problem. So and then a regression problem is nothing but if you're predicting a numerical value. Let us say you're predicting how much of a loan amount can I give a particular user. So if someone applies for a loan in the bank and you run an algorithm, machine learning algorithm, and it says, you can give this user 1,000 rupees versus another user could be 2,000 rupees, versus another user could be 1 lakh rupees. So that is the type of regression problem where there is no yes or no, or there is no particular classes, but it is kind of a discrete set of values. It could be anywhere between 0 and a value, or it could be anywhere between -100 to a +100. So that is a type of regression problem. And then clustering. So both classification and regression problems are handled because you have a predictor variable in the training data set. So let's say you have like 1 lakh rows of data where you have classified that particular data, and then you have another set of test data where you need to perform the classification. So you already have a set of trained data which has classes or predictor variables. In a clustering, it's nothing but there is no target variable. You just have to find out which of the set of rows could cluster and how many could we actually cluster them into. So a classic example could be so based on festivals that are being celebrated, can we cluster users into different categories? So when we consider about festivals, it could be it could be regional, it could be state-wise, it could be country-wise, it could be international, it could be anywhere. But how do we cluster them? Because you don't have pre-labeled data. So it could be like the particular state or the particular country, and when you group all those together, they all kind of come very close together, they form a cluster. And so you say if a set of people celebrate this function and they're from this region, they probably cluster together. So that is something where you don't have any predictor variable, but the model by itself tries to cluster the users into different cohorts. So this has like a wide variety of applications. It could be, it could just depend upon industry to industry where these type of applications are used. So then there is hyperparameter tuning. So once a model is trained, you decided whether it's a classification, regression, clustering algorithm, and then you put in XGBoost, or you put in a logistic regression, or any type of neural networks, or any type of algorithm, and you got a result. So we then need to do hyperparameter tuning to prevent overfitting. So in general, what is overfitting? So when a model is trained, you get a train accuracy, and then when the same model is tested using a different set of unseen data, and if the accuracy drops by over a certain percentage, that means the model is basically trying to memorize the data. So the model is, with the trained data, it's kind of memorizing, if these are a set of features, this is the output. So when it sees a new set of data, it's unable to predict. That's why the accuracy drops. So it's very essential for a model to not overfit. So to prevent overfitting, we need to do this hyperparameter tuning step. So here, if we take any tree algorithm or something, it's very highly likely, because a tree, imagine like a decision tree, or just a binary tree. Okay, you could have n number of leaves, it could just keep growing, the depth of the tree could just keep growing. So if a tree's depth keeps growing at each step, say let's take the first step to be a country, and then under the country, if it's going to be state X, state Y, n number of states, and the tree keeps growing level after level. So what happens is, the model kind of memorizes, if I take this particular route from route to node 1 to node 2, and then to node n, then this is going to be the predictor variable. So at that time, the model tries to memorize the data. But if the model should not memorize and kind of learn the data, then we need to kind of tune it by saying, don't go beyond 10 number of levels, or don't go beyond 5 number of levels. Depending upon the complexity of the problem, we basically need to tell the model not to go beyond a certain limit, or not to go beyond certain number of end lead nodes. So those are some things where this hyperparameter tuning helps us to prevent overfitting. So now once we have a model that is not overfitted, then we have to go to evaluation. So this model evaluation could be in different aspects. So it could be AUC, precision, recall, F1 score, accuracy, and every set of problems has a different model performance metric. So the reason being, like area under the curve is the AUC, that is kind of very common and is kind of a best metric, because it kind of looks into how well the model performs irrespective of the application. But when we look at, let's take an example. So let's take, there is a data set, and you want to predict if a person has a certain disease or not. Okay, so let's take, for example, if a person has COVID or not, right? So what happens in this case is, you may have like 10 lakh rows of data where there is no COVID, but just 1 lakh row of data, or even less than that, to have COVID cases. So in this case, it's about 99% of people do not have COVID, and 1% has COVID. So let's imagine this scenario where you classify all the people as they do not have COVID. So even in that case, your accuracy of the model would be 99%, because you classify 99% of the people correctly because they don't have COVID. But that is not the purpose of the model. So in those kind of scenarios, accuracy is kind of not a good metric. Then comes precision and recall. So one of it is true positives and the other is false positives. So you kind of need to know which is better. Is it better to say if a person who has no COVID to be classified as a person who has COVID? Or is it better to say a person who has COVID to be classified as a person who has no COVID? So in this case, I would prefer the former, because if a person has no COVID and still says he has COVID, that is better, because The disease does not spread out to n number of people. Whereas if a person who has COVID is classified as not COVID, then person may not be isolated. He may spread the disease to another n number of people. So it's important in every applications way, which is an important metric to consider. So it differs from application to application. So now we're going to look into a simple Python code example. So this is a Jupyter notebook. I'm not sure how many of you are familiar with this. So Jupyter notebook is a way where you can write your Python code and run it by cell, and it has it is mainly used in a lot of industries just because it is more easy to access data from the cloud, from different data sources, and use it. So it's a pretty much industry standard tool. So I'm using pandas, NumPy, and a simple XGBoost algorithm. So pandas is generally used for because it is easier in doing a lot of operations with row wise, column wise, cell wise, so it's pretty easy. NumPy is generally used because certain types of array format of data is generally executed, certain calculations are generally much more faster in NumPy, and so NumPy is pretty important. And then I'm using an XGBoost algorithm. So this is a very simple data set that I'm using, which is nothing but a Titanic data set. So this data set has this is the type of data. So it has the passenger ID, whether they survived or not. This is the target variable. So what we need to do with this data is predict, based on the other columns, we need to predict if the passenger who embarked the Titanic boat actually will survive or will not. So as you can see, passenger ID, irrespective of passenger ID has a 1 or 1,000, it is not going to matter. So passenger ID is something which we don't actually need. P class is something we could need, and irrespective of the name of the person, it's probably something we will not use, or it's not informative for us. Sex, male, female, this could be essential because whether they're able, in case of a survival issue, if the passenger could actually jump or not from the boat. So this could be an important metric. We don't want to get rid of that. And then we have age, and then we have some other set of data, ticket data, fare data. All of this may not make sense, but it is still okay for us to use it. But for simplicity purposes, I have not used all of that data. So what I'm doing in the feature engineering part is I'm taking the features that we actually need, which I think will be important, and I'm then converting them into numeric features and categorical features. So when you say numeric features, let's say P class, right? This is a numeric feature. It has a pretty numeric column, and if you need to look into how the data is, you can do a describe. So in this, passenger ID, it has a count, mean, standard deviation, minimum, 25th percentile, 50th percentile, 75th percentile, maximum. It has all of these. So this describe works only for numeric values. So if you're unsure, if there is a large data set, you don't know whether it's numeric or categorical, you can use this describe function. It works very well for numeric features. So you can identify which of these features are numeric features. And then out of the other things, I use categorical features to be just sex. And then I'm just dropping off all the unnecessary columns. So which means I'm just taking only the features that I actually need. So I'm just using from the train data set, I'm just taking train of features. And now I'm filling the missing values. So there could be a lot of missing values in all of these. I'm just, for simplicity purposes, just filling it with a 0. So anything which has a missing value will be filled with a 0. You could fill it with a 1, you could fill it with the mode of that, you could fill it with the mean of that particular column. It's up to you to fill however you want. Whichever makes more sense. And then for categorical columns, this is the place where feature engineering becomes a little tricky. So for a categorical column, the when we say a model like that, you know, category A, B, and C, the model is not equipped to kind of find out if this if a particular column has values A, B, C. It should generally have a numeric value or a 0 or a 1. So we have to convert these categorical columns into something like category A, category B, category C. And then in category A, if that categorical column had a value A, you would put a 1 in there. Otherwise, it would be a 0. And then categorical column B would have a 1 if the actual value was a B. Otherwise, it would be a 0. So you would fill all the categorical columns this way. And I've done the same thing here. And I put a count greater than or equal to 10 because it's possible that if you have a categorical column, let's say country, it has 200 countries. So you have 200 columns. But then in 10 of those countries, there is just 1 or 2 of the rows have values for 10 of those countries, which means those countries are not so much meaningful. You can kind of get rid of those countries. So I'm having a minimum bound that the number should be at least 10. Only if that categorical variables count is more than 10, I would go ahead with creating that particular categorical encoding. And then now I'm filling it with a 1 or a 0 if it has that particular value or not. So now I'm dividing the data into train and test data sets. So the train data set basically should not have, so the train data set basically has the data called survive, that is a target variable. So when we divide it into train and test data sets, it's important that the model needs to know what is the train data and what is the train predictor variable. So I'm kind of segregating X and Y to be train data and predictor variable. And then I'm kind of separating this based on the length of X. I'm putting 60% of the data to be train, and then 20% to be validation and 20% to be test. So I'm dividing that into particular columns, and I'm printing out the shape. Shape means this has the shape of train data set is 534,6 means it has 534 rows and 6 columns. It's very important to make sure the shape of train, validation, test, train plus validation, any of these should have the same number of columns. And it is also important that between each train data set and the train data set target, the number of rows should be the same. So these are some 2 important things that we need to make sure before we go ahead with the classification. So the reason I decided that this is a classification problem is because the survived variable, right? So this column has only 0 or 1. I can do, for simplicity purposes, I can do this. Right. So now I'm just looking into how many people in the survived column have a 0 versus a 1. So if there are more than 2 variables, that will also be listed here. So 549 of them did not survive and 342 of them actually survived. So this is a very, very small data set that I took just for simplicity purposes to run quickly. So now I chose a classification algorithm. So classification algorithm could be anything. It could be a random forest, it could be XGBoost, it could be naive Bayes, it could be any of a classification algorithm. I've used an XGB classifier, and I've just given some parameters. The max depth should be 3, estimator should be 300, learning rate, and I'm just fitting it on X train and XY. So and then I'm doing a predictions, right? So now once this is done, I talked about hyperparameter tuning, where we need to do this because the model should not overfit. So I have given a set of parameters like learning rate, subsample, max depth, and some of these hyperparameters, and I've given a range of values which they could be. And from those range of values, I'm kind of doing a randomized search to find out which is the best parameter that gives the best score for me. So, and I'm doing the same type of, train test split, and I'm doing a fit on the X train and Y train. Now I have this train model which has all the scores of all the type of, so if the learning rate was 0, subsample was 0.3, max step was 3, and then other parameters, for all of those I have what was the mean score. So now I'm printing out what are the best parameters after hyperparameter tuning. So I am just printing out the top one. Okay, I'm just printing out the top value. So 0:1, it just shows us the top value because I've sorted it by the mean test score. So the parameters that give the highest mean test score is the hyperparameters that I actually want to use. So these are the 5 hyperparameters, and this is the mean test score that I got. So now after I got this hyperparameter tuning, I'm kind of retraining the model with the train plus validation data and best hyperparameter. So I'm retraining this model with the whole data set. So now I'm just giving only these hyperparameters that we chose, and then I'm retraining it again. Now I'm printing out what are the top predictive features. In this case, we have only 6 features, but in a large data set with about 100 columns, there could be about 300 features, and all of those 300 features are not something important. So just for simplicity purposes, I've used this data set, but which prints the top 25 most important features if there are. So now you can see that this is the order in which the feature is important. And then now we can see train and test AUC. So train AUC is 0.89, validation AUC is 0.85, and test AUC is 0.88. So when you look at this data, there is not a big difference between train and validation, and there is also not a big difference between validation and test AUC, which means the model is not overfitting. So this, if at all, the validation AUC is 0.85 and then the test AUC is something around 0.7, that is surely something alarming, which says that your model is definitely overfitting. So you probably have to handle hyperparameters much better. So this is a very simple example of how we can go ahead with the okay. So now I want to where do we build these types of models? So whenever we are in the initial phase of model building, right, or we are in the research phase, we don't know whether this model would perform well. We just want to do a quick POC. We want to find out if this model performs well or not. So, and then if we definitely know a model will not be deployed, this is kind of the workflow that we should probably go about with. It could be a normal just a classification regression, could be any type of problem, but this is the general methodology that we want to try to follow. So, but when we know that this model is going to be deployed, right? So we need to modify the code to deploy the model. So now I'm going to show the same code where we put this model into when this model is going to go to production. So I made this also very simple to be in a Jupyter notebook, but in production, you would basically have all of these code into different classes, and the way in which the code is used would be different because it will be in different classes. It could the format would be a little different, but this is the most gist of how the code would be. So the most important part here is adding this imputer classes. So you're loading the train test data, and this imputer class is the most important difference between a model which is not deployed and a model which is going to be deployed. So why do we need this type of imputer class? So in the previous model, right, I just did you fill all the missing values by a 0. This is what I did. But this is not the right way this should be handled, because in production, when you get some data, then you cannot be doing all these things manually, because you're getting a request for a prediction, and then you cannot be doing all of these things manually, because you need to define that this particular feature should be filled with a 0, this particular feature should be filled with a 1, and all of those things. So when it comes into productionizable code, you probably want to put like a numerical imputer, which means these are classes: base, estimator, and transformer mixing. These are classes from the sklearn.base library. So we are importing those classes and overwriting the methods there. So in this type of a case, we are kind of saying we have a fit and a transform method. So the fit would basically do anything that you want to externally do something, and then transform is basically going to use the variables that we used in fit to basically transform your data. So in a numerical importer here, I've just done make the feature value to be NA, like feature value which is null to be a 0, and then return that particular data frame. And here I have not defined which feature, what, or any of those things, right? I have not given any of those specific variable names. That's how I have done categorical encoding as well. So for this, I'm just doing a one hot encoding, a frequency encoding, a targeting. There are different types of encoding metrics that we can do. And I've used the fit and transform here to basically do that particular code. So you can see most of this code is what I've used here, but in a slightly different modified way. And then drop unnecessary features. So in this place, what I did was I was selecting all the necessary features. So train is equal to train of features. But here I'm writing a class which would basically drop all the unnecessary features. I have not defined any of these features in these functions. So it is only here I'm dividing the train and test data sets. It's only here that I'm defining. So I'm defining all the unnecessary features, categorical columns, and numerical columns. And the next important thing is I'm creating a pipeline. So what does this pipeline object do? So this pipeline object basically tells step 2, step 3 in the order it has been defined. So now this pipeline object has been told to do numerical imputer first, followed by categorical encoder, followed by drop features, followed by building the classifier model. So here what happens is the numerical imputer, I've given the variables to be numerical calls. So this is going to be all the numerical variables. So when all the numerical variables here is used in a pipeline, for all those variables, this particular numerical imputer class would be called, and so the data would be transformed. That is what applies with categorical encoding and drop features as well. And then I've also put the XTB classifier in the pipeline. So now I do have a pipeline object, and I'm doing a randomized search on this pipeline object to find the best parameters. So now this is how my output looks. So it has a randomized search, and then it has a pipeline object which has all of these classes defined inside. Whereas this did not have anything of that sort. It just has a classification model, and then I am printing out all the best parameters. But here there is already a pipeline which is fed with data of what should be done and when it has to be done. So now the other steps are remaining the same. Now we got the best parameters. We're retraining it on train plus validation data. And then now I'm printing out the results of the randomized search. So this is the whole set for all the set of parameters that we gave in this randomized search, right? So we gave a list of parameters. For all the list of parameters and combinations, we have this table with each of the column names and the mean test score. And then now this is the best column. I have sorted this by the mean test score. So this column has like the best hyperparameters. So then we need to do the same type of predictions, and now we got the train, validation, and test AUCs. So this is how the code would differ from research phase into deployment phase. So these are some industry standards which you can use even while developing models which are not in the deployment phase, but would be good to use. And it is not very complicated. You can use it in the same Jupyter notebook. You have functions, and there are like tons of ways where you can use all of these type of imputer classes and create pipelines for all of the data science ML work that you are doing. So coming back, we modified the code to deploy the model. Now I'm going to talk about the intersection of data science and data engineering. So as a data scientist, we always spend a huge amount of time in improving the AUC of the model and improving the score of the model, because if the score goes from 0.88 to 0.89, that is a huge improvement in terms of AUC for a data scientist. So, but when we need to put these models into production, we always need data engineers, because it is not possible for a data scientist to completely put all these models into production. We can create the code which needs to be in the order so that we can put it into a model. So, and one very important thing that I forgot to tell is, like, once the model is done, you have to convert this whole pipeline object into a pickle file. So there's something called import pickle in Python, where you can convert the particular Python object into a pickle object. It is just like it would get converted into a small .pkl object, which can be used or which can be put into any other system and can be used for predictions. So, okay. So when we come into this deployment phase, a model pipeline that I told, that is which is pickled, that is the end product for a data scientist. So how, let's say, like, we have one particular pickle file, and now you have to use this pickle file to make predictions. And and how this works is, if I send a request through my app, okay, through a mobile application, it needs to go and hit the server, and it needs, with all the details that the user is sending, and it needs to query that particular pickle object, and get the score and return it back to the user and say what is the prediction. So for just a small mobile application which needs a machine learning model put into production, there is a lot of complexity in this. The reason being, we give a pickled file, but then what is happening? You need a particular server or a particular place where the pickled file needs to be deployed, so that the request from the user can be sent, and it will be like an endpoint. So just assume that you are hitting from the front end, you're sending a set of requests, you're hitting an API, and the API is returning back some results, right? So in this case, the API should be a pickled model, and this should basically return any requests of predictions and return it back to the user. So this is a complicated process. So now, how can we create this particular API? So for this purpose, this pickled model is generally put into a Docker image. So what is a Docker image? It's just like a virtual environment. But in a virtual environment, you need to set up, there's a lot of things. But in this Docker image, right, it is also set up, but it's pretty quick. And this Docker image comes with preloaded libraries. So let us say that the Python version that I use to build my model is Python 0.23, right? And if I put this model into a machine where there is Python 1.3, right, there is a version conflict. This model will not work as we expected. So it's very important that all the versions that were used to train the model is the same that we are using in production. So with all that versions of packages that we are using for training the model, we need to develop a similar virtual environment which is pre-configured with all of these files, so that instead of using a virtual machine, we're using a Docker image, which is much more faster, simpler, and easier to use, and very easy to be integrated into industrial standard tools. So in that Docker image, we are basically putting this pickled model. So once this pickled model is put into that particular Docker image, we are creating an endpoint, like an API, where any request from the user would hit that particular endpoint, and it would with a set of columns, it would basically request the pickle file for predictions. Pickle file would give a set of predictions, and it would, based on that prediction, so let's say the pickle file basically predicted 0.89 or 0.98 or something like that. So then it is the app that basically, there is a process which basically decides whether this user should be approved, this user should not be approved, or this user has a disease, or this user does not have a disease. So it depends upon that prediction score. So that is done, and then the final result is communicated to the user. So for all this whole purpose, we need a lot of data engineers, because there are like a ton of challenges that are faced during deployment. So one thing is, we need to make sure that no requests fail because of mismatch in data types. Let us say that we want to predict how much of what do I say? How much of money can I loan a particular user? So if I need certain amount of data, like certain columns of data basically, and they should be in certain types. Let us say for a integer type column, if the user data that comes in is a variable, is a categorical variable, it's like a sentence or something like that. Okay, so if something like that happens, the model will surely not be able to predict. So there's going to be a data type mismatch, and so this request is going to fail. So we need to make sure that none of that happens while the model is in production. So whatever comes should be as expected, and whatever the data the model gives should also be as expected. Another thing is response timeout is very less. So this is a very important thing. So when, as a data scientist, we generally try to concentrate on improving AUC. So let us take two models. Let's take a XGBoost model has an AUC of 0.889. And then we have another classification model, which has a AUC of 0.885. Okay, and then we have another neural network model which has a score of 0.9. So out of these, we would probably choose neural nets just because the AUC is high. But then when we look into complexity and time taken for a particular request, right? The time and complexity for a neural net could be higher than a XGBoost. So for a cost of 0.01 in accuracy, we are losing a lot of time on, we are losing a lot of money on complexity and time. So it could be possible that whenever you request or whenever you send a request in a application, you probably want the result as quick as possible, and the user does not want to wait too long. So there is generally a timeout which is like 5 seconds, 10 seconds, 20 seconds, depending on application. So it's very important that the model that we put in production is good, which has a fair which acts very fairly with respect to the time taken and accuracy. You don't want to take a model which has takes too much time and good AUC versus a model which has a good AUC and lesser time. I would choose the model which has good AUC and less time, because that is very important when we put models into production. So, and then it's highly possible that the prediction score that we did while testing the model, right? So I built a model in Jupyter Hub, Jupyter Lab, and then I kind of tested, I got prediction scores. So I have a set of prediction scores. When I use the same set of requests in production, my prediction score could be different by even 0.02. But if that is the case, that means there is some difference between the environments in production and in while we are testing out the model. So we need to make sure the prediction score is exactly the same to a nth point. So it's very, very important. And we need to make sure we're handling batch processing. So whenever we try to evaluate, data sets, we try to take test data sets as just one whole chunk. We put it into the model, we predict scores. But in production, what happens? Requests come from different, millions of users send different requests. We need to handle all of that. So it could be very time consuming for sending just one request at a time. But if we could process it, say 100 or 1,000 requests at a time, it would be beneficial for both the user and the server, because the server would not time out and it would not fail or not crash. So that is very important. So these are some of the challenges that we face during deployment. So for these purposes, we definitely need data engineers to help out. So this is a small visualization for what a data scientist could do and where a data engineer can contribute. So we spoke about all the data scientists. So with respect to data engineer, they look into how and where to do the data storage in an efficient and proper way. They do all the DB administration stuff because it is very important to build a secure system while deploying a model. System implementation basically includes what happens or how does a request basically go into an endpoint, and how does it return the result, what needs to be done, how to do A/B testing, all of those stuff comes into system implementation. So there are a wide, there is quite a big difference between data scientists and data engineers, but we need to work together to basically make this a proper model which is deployed into production. So, right. So now coming to methods to monitor a model performance in production. So now we put this, assume we put a model into production, it's working fine. How do we actually monitor if the model is actually performing well? Because when you tested the data, it was performing well, and when you tested the same data in production, it was performing well. But what happens when there is new data? So there are certain ways that we need to monitor the model performance. So let us say the AUC value trained the model was 0.89, right? And then you need to keep monitoring what is the average AUCs of all requests on a daily, weekly, monthly basis. So if the AUC is less than the 10th percentile or greater than the 90th percentile, then that could be of concern, which means that something is wrong and we probably need to look into it. But the AUC on any of these bases is between the 10th and the 90th percentile, we are still good. There is not a big degradation in the model performance. So it's very important that once we put the model into production, we need to build a data monitor along with that to see how the model is actually performing in production. So here is a small graph that I put. So you can see that the dark blue ones are the training AUCs, and the light blue ones are the production AUCs. So let us say the AUC is generally between 0 and 1. So there is no missing data, there is no less than 0. So you can see while training, maximum number of people had AUC between 0.9 to 1. And while in production, you can see that more than 65 to 70% people are having AUC greater than 0.9. And then you can see that the AUC is in the range 0.7 to 0.8, 0.8 to 0.9 have all reduced by a few percentage. So this is an example of seeing a little change in the distribution of AUCs and the percentage of records and the distribution of AUCs in training versus production. So you need to make sure that how much of a difference in this is acceptable depending upon industry to industry. Right. So next is data drift. So let us say the previous graph, okay, we found that there is some difference. So there is something that is different. You need to identify what is different. So when we come into that aspect of what is different, in general, which could lead to a difference in the prediction scores, is nothing but the features that we used for the model. So you need to see how these features drifted to basically create a difference in the drift in the AUCs that we predicted. So if either one feature or a set of features distribution differed by a large percentage in comparison to what we had in the training data set, that is what we call as a data drift. So let us say that for a prediction, for any prediction application, let's say we had this feature called age. So this age distribution in the trained data set, say 60% of the users lied between 20 to 40, and then the remaining 40% of the users could be less than 20 years or could be more than 60 years. And suddenly we saw that the data has, there is a highlight, there is in the data monitor, some things are drifting. So when we look into that particular age bucket, now there are only 30% users in that particular age group between 20 and 60. The other 70% fell either less than 20 or more than 60. So that shows that there is a significant difference in the data that we use to train the data and train the model in comparison to what is actually happening in production. So this could be, when can such a change happen? It could be because of three reasons. One is data change. Let us assume that something in the application happened and all users less than 40 years were bucketed into the 20 age group. So that is a significant data change, which could be an error, which could be on purpose, which we do not know of, and that has caused significant changes in the data. So this is one reason. And then second is change in behavior of users or cohorts. Let's say first this application was trained on the users in India. And now, because of some expansion purposes, this application is being released to other parts of the world. So now this application is seeing data from UK, Europe, Asia, Australia, all other countries. So what happens is there could be different behavior of these cohorts of people. So people in Asia may behave differently to the people in US or the people in Australia. So there could be a significant change in the behavior which we are not aware of, and this could create a large difference in the data drift. The third is unprecedented events. So you don't know, you cannot guess, you don't know why this happened, or you don't even you don't have a say in why this could have happened. Say COVID, no one has a say in why COVID happened, for what reason COVID has. So this COVID is an unprecedented event. It is a pandemic. So you don't know how users' behavior will change during a pandemic. So as an example, during this pandemic crisis, users probably saved up more. People did not spend too much money. There was no entertainment. Entertainment industries were closed. So people did not spend on entertainment. Then, it's possible that people spent mostly on food. They did not spend on outside food, but bought groceries to cook. So there are a lot of things which could have, whose behavior or pattern could have changed significantly just because of an unprecedented event. We had a lockdown, so there are everything has closed. So this is something which no one in the world can predict or can have any information about how people's behavior will change. But this data that we collect during this pandemic is extremely important. If we are having another pandemic in 100 years from now, the data that we collected today will be very important during that particular pandemic, because we know that previously during pandemics, this is how data has been, how people have behaved. So that's why we say data is extremely important, extremely beneficial, and we try not to waste any type of important data. The next is so when we look at data drift, right, only if there is a drift in the prediction variable, only if there is a drift in the in the values of the prediction variable, in the accuracy, AUC, or any of those evaluation metrics, only if there is a difference, we look at what caused that data drift. So that is a very important point. If there is no difference in the prediction variable, there is no need to see if a feature drifted or not. So this is one of a message. Let's say it's a WhatsApp app. This app is trying to classify spammers from non-spammers. So in this region, right, it was pretty easy to classify spammers from non-spammers because their patterns were different. But after an app update that happened in the 40th second, right, the model is unable to predict it's a spammer or not spammer, just because the pattern has totally changed. See, the number of messages sent per minute for non-spammers has gone up to 20, which is generally considered as spammer. So the model gets confused. And this is an example of when data drift, looking at data drift would give you an idea of which feature caused it. And then you can kind of go and see if there was a data change that happened unknowingly or knowingly, and kind of look into what can be done to rectify this. Right. So we've come to the last part of the segment, which is industry standard tools and technologies. So this is a set of tools and technologies which I've grouped here. Could be used for a different variety of purposes. Tableau is a reporting tool, is an analytics tool, and this is industry standard. You do have a free trial version for a few months, but then it's paid and it's extremely expensive. So this is used in industries, but would not recommend it for research purpose or anything. Looker is another. Looker and Mode, these two are another extremely useful reporting, dashboard building, or analytics tools which are used in industries. The reason these two are pretty good is because these connect with any of the cloud platforms, with any of the data warehouses, and so accessing data is extremely easy with either Looker or Mode. So, and these are, I am not extremely sure about, these are not open source, so these are paid resources. ClickView is also is a visualization tool, and but this is comparatively less expensive. And Data Wrapper is one of the tools which is open source and is a very good data visualization tool. It is free of cost. So this is something which could be interesting to a lot of you. And then comes ggplot and Plotly. So ggplot has is an open source tool as well. It has extremely good different plotting. You can create different plots with ggplot, and you can also make it look more beautiful because of the simplicity in adding colors or textures or beautifying your plots. So that ggplot is extremely useful tool. And then Plotly has a paid and a non-paid version. So the non-paid version has like X number of requests per day or per week or something like that, but this is also a pretty useful visualization tool. So I think I covered all of the visualization tools, right? Next is the data warehousing tools. So Snowflake is one of the emerging and important data warehouse tools. This is primarily uses SQL, but has little different standards in SQL. And it's very easy to use, and it's extremely integratable with any of the visualization tools. And then we have Google Cloud and AWS. So they are like, and then we have IBM, we have Microsoft Azure, which are all big cloud companies, and they provide huge infrastructure on data warehousing and then data storage, and and at different levels. So when data is being used very frequently, they have a particular data storage method, and then when data is being like not used but maybe used very occasionally, they have certain types of data storage. And then some data you don't need at all, but you're just using it for storage, you're not going to access it on a daily basis. They have different types of storage methods for that. So I mean, all of these are emerging tools, and all of these, Google Cloud, AWS, Microsoft Azure, and IBM, have a free 1 year usage. So if you can sign up, I think the first 1 year is free. Or GCP has like, if you can use all the resources up to you spend $300, and after that it's you have to pay, but till then it's pretty good. So they have like, all of these main softwares have like pretty good sign up advantages, and you can play around with all of these things. Yeah, next is Jupyter. This is what I've been using: Jupyter Hub, Jupyter Lab, Jupyter Notebooks. This is mainly used for Python or R, pretty extensively used in industries for development purposes. And yeah, Apache Spark is one of the ETL tools that I mentioned. It's extremely popular, getting more popular every day. I am not an extreme ETL person, so I am not. I don't know how much of Apache Spark is useful, but I know it's pretty emerging. And then we have deep learning tools, TensorFlow and Keras, which are all completely open source. So it's free to use. And then scikit-learn, NLTK. So scikit-learn is the are all the packages that I've been using for classification and regression. And then NLTK is the like the language processing tool. So if you have text data, let's say Twitter data, it has a lot of text. You want to find out if a user is sad or happy by a particular post, like sentiment analysis. NLTK is probably the tool that you want to use for truncating, dividing all of these data into smaller parts, and using that for training. So NLTK by itself is a whole different course. So that is, and it's pretty interesting, and also an emerging field. And then comes data robot. So data robot, I don't think they have a free version, but with data robot, the thing data robot does is you can feed in all the trained data that you have. Data robot would do all the modeling for you. It would give like X mod, let's say 10-20 models, and it would give different AUC scores, and then you can see which model is the best suiting for your application and deploy that. So for a company, or which does not have data scientists, they're in the preliminary stage, data robot is like something which is handy for them to use. So yeah, that is a tool which is probably interesting as well. And then BigQuery is a part of Google Cloud. So that is, BigQuery by itself is something similar to SQL, but has a little difference in syntax. But BigQuery is very interesting to use, because with BigQuery, by using a query, you can actually build ML models. So it's a different way where Google Cloud has integrated BigQuery, and the way where how you can use these ML models is very good. So but there are just minimum number of what do I say, algorithms that can be used, properly limited to logistic regression, linear regression, and some classification algorithms. But it's something that you can explore, and it's very interesting. Apart from this, we use GitHub or Jenkins, which is version control libraries. And I think it is also, GitHub has a free version. So I recommend anyone who are writing code to check in code into GitHub, like look at a YouTube video tutorial about how to use GitHub. It is the version control and extremely useful for companies who actually want to hire data scientists or data engineers or even software developers. They can kind of see how much of code you have actually written. So it's extremely useful. I recommend everyone to look into how to use that. Yeah, so I just put in some useful links. You have a ton of machine learning courses in Udemy. You have a ton of machine learning courses in Coursera, and then a lot on YouTube. So the number of resources is totally unlimited for machine learning, for deep learning. And scikit-learn is what most companies who want to build and deploy models use. So I just put that into a tool. Kaggle. So Kaggle is a data science competing platform. So let me just toggle. So Kaggle is this type. So it has n number of data sets, and then for any okay, let's go into compete. So there are a lot of competitions. So let's say if I want to predict future sales, this is a competition that I have enrolled into. Then you can see where the data is. You can get a description on what this data is about, and then you can look into the data. And they do have like sample files, train, test. They have like a lot of files. And then Kaggle provides the environment for you. So you can create a new notebook, which is a Jupyter notebook, and use and access all the resources that Kaggle offers. So Kaggle also offers TPUs usage which is free up to a specific limit per day. So this is extremely useful for deep learning algorithms, where you would not be able to set up a machine with TPUs and everything, which is going to be very which is going to be very expensive for all of you. So this is one thing. And the very important part is discussions. So in this discussions, it's like though you don't do anything or you don't know how to do it, you can still look at, a discussion from someone. They kind of like put into, it's just a platform where you can ask questions, people reply, people respond, and it's a discussion platform. And then you have this leaderboard where they have a team name, they have team members, and this is the score. So the team with the highest score is, or the team with the highest score in the final competition actually get their name in here. So where do you stand. You stand the 1000th place, or do you stand the 2000th place, and what other people are doing. And this is a team game, so it's like a lot of you can team up. I think up to 4 people can team up for a particular competition, and you can all work together. So Kaggle is a extremely useful tool, which is free, and they provide tons of data sets. Data could be image data set, fintech data set, health data sets, what else, it could be image, it could be natural language processing, text data set. So there's like any type of data set that you actually want to use, you can use it from here. And the data set that I used for the Titanic data set was also from Kaggle. So from various sizes, from various um, companies, institutions, they have lots of free data sources. So this is an extremely important tool I would recommend everyone to take a look at. So yep, I think I have come to the end of my presentation, so I'm leaving it to Q&A now.